Hi, my name is Keenan Hardard. I'm a professor of biology at Minnesota State University. I study cancer research and education research. But today we've got the Prism tutorial data of the Titanic. Yes, so we've got 0 or 1 category if you survived or didn't. 1 is a survive. We do have some continuous quantitative data. How old was each passenger? Were they male, first class, or second class in this case? So the good news here with multiple logistic regression, you're dealing with something where the outcomes are binary. They happened or they didn't, and that's it. So we have that set up as zeros or ones here, but it can also handle continuous data like this. Now, our variable here, dependent, is survival. So what we're going to see is we're going to compare the actual zeros and ones here after we run the model and say, based on the strength of each of these factors, can we predict who would have actually been a 0 or 1? Let's say like we've kind of rerun the simulation. And if these stats right here and these data are good fits for predicting who would have survived and not, the model can tell us that. You'll also notice that with logistic, we can't do a linear regression here because we don't have multiple continuous data, and you would never use a 0 and a 1 in like a straight line style regression. All right, so let's go here. We are in multiple variable right now. This is what's going to be able to handle it the best. You would go down to multiple logistic regression. We can have everybody signed up. Let's hit OK. In this case, we want survived. And again, our positive outcome is yes, that we did survive in this case. For the reference level for each one, let's decide. I'm going to keep reference level as male, yes, because you're going to see I don't think that works out very well. Let's say that for reference level, we also, yeah, I want to say that the reference is yes, you were a first class. And for second class, I also want to say, like, we'll call that a yes, that you were a second class. So this is mainly just going to kind of help us when we spit out the numbers, it's going to be a little easier to follow. In this case, we can go ahead and add some columns here. I usually add a p-value here for the best fit for parameters because I like seeing that. Correlation proportion correct versus cutoff, not bad. So let's go ahead and run this right here. Nice. Okay. So first setup that we're going to see, it is going to give us a lot of numbers. So remember that beta and parameter estimates are basically going to tell us, all right, for the log odds change, if you increase 1 unit of each of these units, for example, what are the log odds increase basically in that direction? So given that the reference was you were yes a male, now we're saying, okay, if you were not a male, for example, actually got a little better, right? You went a little higher towards that good survival area because you went up for per unit. Um, Given that it was not a good thing then to be male in this case and have a 1 next to you. So looking over here, were you first class? And in this case, this is a 0, so this is saying you were not first class. For being not first class, you're going to go down in terms of the log odds that you have of making that +1 outcome. And then if you were not second class, same thing. It's a negative, it's like a bad direction basically for what we're seeing. So looking down here for odds ratios, these are a little more like kind of like how survival curves produce odds ratios. Age didn't do too much, but I assume it was predictive enough to have some estimate power. But again, the ratio isn't huge. But you can see right there, the ratio is pretty tight that it's not going to be great basically because you're below that ratio of 1 that you want. So again, looking at were you male, or sorry, yeah, because it's not going to be great. So it's 12 times, well, let's say for every 12 that were this, 1 that didn't, basically, for the odds ratio here. So in this case, if you were female, because male's 0, you're doing pretty well at getting to that 1.0 survival. So for every time that a male did make it, 12 non-males did make it in that case. So the reciprocals down here for first and second class also look pretty good if you were not part of those two. All right, so significant difference for 0, kind of your basic setup for was the model predictive enough? Did it contribute to the model enough significantly that we would delineate that like, hey, this was powerful enough. So even though age had a smaller value when we saw it up here, it still was tight enough and, kind of with the model enough that we did well. So most of you are familiar with logistic regressions, where the area under the curve is sort of like how well did your model build? This is going to be this ROC curve right here. So 0.83 under that is pretty phenomenal. The ideal would be like a perfect one, but that's usually not possible with raw data. So the further it goes up in this direction, the better the model. And we do see that with, obviously right there, we actually do get a little p-value to say like, hey, my model worked. So that's good. One of my favorite little setups here is it's going to say, all right, based on all the data that we actually have predicted versus observed, how good were we at this? So predicting non-survival, we correctly classified with this model 85% of the time, and about, yeah, 68% of the time when you did survive, for example. So not too bad. Got a pseudo R squared, and Hosmer-Lenslau is going to also say again, how well did this model predict and fit, essentially? The Z that we also got this from is not like a Z score in the same way. It is built off the odds ratio again to say like, hey, did this contribute and pull or push either direction well enough? All right. It's also going to produce some decent setups for us, proportion classified correct, and kind of where the cutoffs were, as well as this one's always going to be a default that it makes. So if we did observe one, how many were predicted to be one? And you can see like what like prediction range there were. Since this bubble is much bigger up here, we can see that, yeah, predicting that they would survive was pretty well done. And like we saw about 60, what was it, 68% were actually predicted to be right. We saw that this non-survival observation, see how this one's much stronger down here at the violin. This one we saw it was like 88% correct or whatnot. So taking a look again over here, curve looks good, but one of the best, coolest things that this is going to produce for you is all this data right here is kind of the overall setup. But the row prediction, now you have everybody in each of these rows. You have their actual survival. Like, did they survive, number one? But based on the model, how close, what was the prediction for them? So as you can tell, a lot of these ones that did survive, like these two right here, yeah, their model set them up that they were like likely survivors, right? You did have a survivor right here that did, based on their stats, did not have a huge chance at making it. So row 11 would actually be worth investigating. Hey, how'd they get off that ship? Same thing you're going to see right here, though. A lot of the times, though, since this was a pretty good fit, especially for non-survivors, see the people with zeros and see how low most of these predicted survival setups are just based on, hey, what'd you have here? So this was who we were just at. This is a young man. He was a male. He was not first class. He wasn't even second class. This is kind of like Jack from the Titanic. He did not survive. So that's why you can go back in time and look and say like, hey, there's row 3. He did not have a good predicted survival. Dang it. But this is really neat. Again, I can use this in cancer research. I use this in education research for pass fails, stuff like that. So a really great tool and another capability of Prism's new multivariable setups. So thanks for watching.